Guys, this is our new boring topic for today. It is called special cases and relative motion, and it is the motion of several particles. Unlike our previous topic before, our topic covers only one particle. Example is a vehicle moving. Of course, if a vehicle is moving, there is an acceleration and a velocity. But for this, there are more than one particle, like M, C, E, W. They are particles. Of course, our term for particle for this topic is pertaining to objects as well, like vehicles, like weights, like elevators, like points. Okay, so our problem here is how to solve this kind of problem. It's hard to solve this kind of problem, but since they are moving, expect that they are having acceleration and velocity. Each one of them is having those properties. But of course, we cannot solve this problem if we only rely on the physics formulas, on the given acceleration and velocity formulas. But we can only solve it if we find other formula sources. So for this one, if the elevator E goes downward, W will go upward and C will go upward as well, but M will never care. It will increase in length only. But if you watch this, if you notice, there are two ropes. The first rope is from M to this fixed attachment, then the second rope is carrying W. Okay, so how do you solve this, guys? Actually, I already wrote 3 steps. First step, generate the equation from the rope length condition. Second step, use physics formulas and then solve. Okay, that's it. That's all. Of course, if we are covering only one particle, we only need the 2 steps, the second step and third step. But since we have more than one particle, and if one moves, the other moves as well, of course we need the first step too. Okay, so if E is going downward by 4 meters per second, expect that W will not move by 4 meters per second and point C will not move upward by 4 meters per second, because the object E has 3 ropes connected to it, and W and C are only along one rope. So expect that they are not possessing the same velocity as particle E. So in that case, just follow the first step first. So in this first step, you need to understand that the rope length is constant. What does that mean? It will never change, because rope is not, here we are assuming that the rope is not elastic. It's not increasing in length miraculously. So ignoring this point M, if we start our rope length from point C to the fixed support here, this first rope from point C to this, the length will never change even if they move. If particle E moves downward, of course the length from point C to the fixed support will never change. It will always be constant. Now, how do we write that? Write it like this way. So the length of this point C to the pulley here is, there is this length. Then we will add it to the rope around the pulley. Then add it to this rope here. Then add again to the rope around the pulley. Then add it to this rope until the attachment here at the ceiling. And it will never change. Even if the objects move, the rope length will still be the same, as long as you are strictly following strictly abiding with the rule that point C to the ceiling only. So how do we solve this? Anyway, just okay, just add the rope length, but we cannot add them all. We do not know the pulley length. We do not know the other lengths of the rope. It's not given. That's why what we will do is that ignore the constant length of the pulley, of the rope. I mean, this rope is in a shape like this, and you can notice the constant lengths. As you can see, the length of the rope around the pulley, the rope length around the pulley is constant. It will never change. It is, you can actually ignore this in your computation. And also this other pulley rope length, the rope here, even if the objects move, the rope length here will never change. Even this guy, the gap between the pulley and this ceiling fixed support is constant. Even if object E and point C move, the gap will never change. That's why ignore the constant lengths. Ignore them, okay? So ignore the pulley length. I mean the rope around the pulley, and then the gap. Ignore those, and then the gap between the ceiling and the pulley. Ignore that, because for now we will generate an equation reckoning from the ceiling. So we will use the ceiling as our reference point for our particles, okay? So how do you write that? First, if you reckon point C from the ceiling, our length we can call it x sub c. Even if point C goes upward, its length will still be called x sub c. We don't care. We're just reckoning from the ceiling to point C that the distance is that way, okay? So, and then plus from the ceiling to point E. You know, if point E is moving, this rope is not talking about point C, guys. It is pertaining to, it's corresponding to particle E. That's why we will call it x sub E, not x sub C, because if E goes downward, the length of the rope at this point will increase. So we will call it x sub E because it is changing due to particle E. How about this last rope? If particle E goes downward, expect that this rope is increasing because of particle E. So since this is increasing because of particle E, expect that we will need to add another x sub E. Okay? And these three distances are pertaining to the points. Even if they move downward or upward, they will still be called x sub C and x sub E. And then, yeah, this is the constant length. This is equals to constant, guys. Because if we add the lengths by reckoning from the ceiling, even if they move, you know, from the ceiling to point C, even if this goes upward, and you know, add it to the another rope. Of course, this is one rope. Since this is only a single rope, expect that even if it moves from point C to this fixed support, will always be a constant length. Try to simplify. Then actually, guys, for this case, you do not know what is the constant value here, but you can actually derive this one, differentiate. If you differentiate, of course expect that the constant will turn into 0, and then this will become v, and this become v, because actually I derived this like this. If you cannot imagine this shortcut, I actually did it like this. I derived it in this way. Yeah, so d over dt. So if x is derived like dx, of course expect that there is a dt. So it is dx dt, and dx dt is velocity. And then another, differentiate again this velocity equation. It will turn into what? Acceleration. That's it. So it's actually somewhat easy to generate an equation from the rope length condition, and it depends upon the system of the rope if it is simple or not. Okay, next, this is only for the first rope, guys. So moving on, use the physics formulas. So for VC, we know that the formula for VC. Wait first. Okay, so actually we can now actually compute for the VC without using the physics formulas, because we know that our VE is 4 meters. It's already given, 4 meters per second. And then of course it will become 8. Actually, it is negative 8 meters per second if you transpose 8 meters per second to the other side. But I will use it, I will not put a negative sign because it's just an indication of the direction. As you can see, if E is going downward, that means that 4 meters per second is positive if it is going downward. But if it is going upwards, then our sign is negative. I'm just going to put here upward. That's the answer. Okay, so for our second step, we don't need this. For now, we do not need it. Do not need it. Solve. Well, we do not need this. I already solved it. Next, so our B. For B, the velocity of the counterweight W. How do we solve that? For the W, you know that it is attached to the second rope. So we need to generate an equation from the second rope. So using the previous concept, we will reckon the distance of the particles from the ceiling again. We will always reckon our particle location from a fixed reference, guys. Fixed reference that is not moving. Of course, we can actually reckon from a moving particle, but it has a different approach. But for this one, we will reckon from the ceiling and it will never move. So the location of point E from the ceiling, using this first rope here, if this particle is going downward, expect that this rope here is increasing in length. Why is it increasing in length? Because of particle E. It is going downward, so it is changing in length. So since it is the cause of its changing in length, we will call the distance of particle E through the rope, the first sub-rope, call it XE again. Then plus, because we are actually summing up the rope length except the constant length of the pulley. Okay, and then the gaps, we do not care about those. So after that, we will add the x sub w. Why w? Because if w is going upwards or downwards, the rope at this point is also changing in length, but the total length of them will never change. It will stay constant. So if you add them both, they will remain constant even if they move. If you add them, even if they moved, add the length, it will still be the same, because the word constant means parehas. Kahit anong mangyari, still the same. And if you differentiate this, I will make it into shortcut because I believe you already understand the concept. If you differentiate, the constant will become 0, and then x will become v, x will become v, that's it. And then solve for VW, counterweight. So our VW is, since VE is given to be 4 meters per second, they are equal, okay? But the direction is upward, of course. If particle E is going downward, then expect that the counterweight W is going upwards. Let me check. Of course, there is only one rope, so this is XE plus XW. That's all. So next is C, the relative velocity of the cable C with respect to the elevator. Okay, I'm going to explain what the hell does the relative mean. Okay, once again, relative velocity with respect to the elevator. Oops. So how the Carabao? How do we get this? The relative velocity of the cable C with respect to the elevator. The meaning of the relative velocity is the displacement, the vector difference, the vector difference between the 2 points. Okay. So the difference between the velocity of cable C with the elevator E is just like this. Subtract the two. So V velocity of cable C with respect, that means that we are putting E as our denominator, with respect to E is equals to VC minus VE. That's what it means. But since this is my introductory video, if you encounter something like there is a given like the velocity, let's say velocity C is moving along the y-axis and velocity E is moving along the x-axis, the relative velocity between the two is the hypotenuse. It's the difference, the vector difference between the two. So it is not actually directly subtracting. If they are along the, if one of them is along a y-axis and one of them is along the x-axis, the relative value is when you get the hypotenuse. The hypotenuse is the relative value, okay? But for this one, since they are along the same axis, you know, the velocity of C with respect to E is they are actually moving along the y-axis, both of them. Just subtract the two, direct subtraction. Okay, so VC, our VC is given to be 8 and it's upward. Our VE is what? Downward. Yep, 4 meters, but it's downward. So how do we handle that? expect that since our downward is positive, then we will make our 8 meters negative because it is upward. So our answer must be negative 12. Okay, let's just put negative 12 per second. We can actually put that because we are talking about relative velocity. So actually, I think our sign is important if it is the relative velocity, okay? Because we are just showing that we subtracted the 2. Okay, so actually that's it. I'm just going to check my book if my answers are correct. Actually, how do you check this? To our book here, check it at the end of the page. You can find it here. And our problem is we are actually solving number problem 1147. 1147. As you can see, this is 1147. 8 meters upward. So our answer must be 8 meters upward. Yes, I'm correct. So next is 4 meters upward. Then 12 meters upward. Okay. 4 meters upward. And another 12 meters. Oh yeah, we didn't yet answer letter D. As I said a while ago, negative is upward. So yeah, I apologize. Let us not make our answer with sign. It would be better if we provide our direction. So we will put here 12 meters per second, but upward. And enclose it with a black box. Next is D. So our D is the relative velocity of the counterweight with W with respect to the elevator. Okay. The elevator is symbolized as E. Now, we'll do the same. So the velocity of the counterweight W with respect to E is equals to VW minus VE. That's how simple it is to solve the relative velocity if they are moving along the same axis, okay? So our VW is equals to 4. It's upward, so our VE is actually what? 4, yes, but it is downward, unfortunately. So let us make our upward negative and our downward positive. So negative 4 minus 4. And our answer will become 8 meters per second. But no, we will not allow that to happen. We will change our answer unitless. And this means upward, of course. And if we go back here, 11.47, our answer is 8.0. Upward, so we are correct again. So actually, this took me 23 minutes to finish this topic because it's hard to introduce this topic. Okay, so I hope you got it. Remember that the relative value is the vector difference between the two values. If they are moving with the same direction or the same axis, with different direction or different axis, expect that you must get the hypotenuse or the length between the two, like a hypotenuse, because it is not necessarily a hypotenuse, it's the diagonal line, that is the distance between the two in terms of the diagonal distance. Okay, so that's it, guys. Of course, if you are solving the relative velocity and the two velocities are moving with different axes, they are not the same, you must also solve for the angle of the hypotenuse or the diagonal line. Okay. Remember that. So that's all. So thank you for watching. See you on next video.